And now we have rotation. And looking back at this picture, we have masses at radii ri. So we have our angular momentum is our momenta of all these small particles times pre-multiply vector product with r. So this is the definition, right? So let us now have a look how this thing actually looks like, this momentum, angular momentum. So we want, in a second, we want to use a dynamic law, right? We had the dynamic law for translation here, and here is the dynamic law for rotation. Derivative of the angular momentum equals to the sum of external torques or moments. Okay? So this h thing is this. Now, velocities, okay, can be written down as angular velocity times radius, right? So if we look at this picture here, okay, so velocity of any point will be angular velocity of this thing multiplying the arm, right? So this we know from primary school. So if we look at this, we can, without any derivation of any equations, we can see that we have a vector of angular velocity multiplied by something, which I have here in blue, that depends on the distribution of mass, right? Masses and radii on which these masses are placed. So this thing is a distribution of mass, and this is the vector of angular velocity. And actually, the derivation will follow that this thing can be assembled into a matrix called inertia matrix, which is a 3×3 matrix. So we will have our angular momentum being equal to a 3×3 matrix of inertia that depends on the distribution of mass, okay, times the angular vector of angular velocity. Okay, so this is so far, I suppose, not particularly controversial. But the controversial or maybe a difficult thing pops up now. Because if we want to take the derivative of it, the green derivative, right, to use the dynamic law, so we want to take the derivative of this, right, this times this. And we would ultimately want this thing to behave the same as this, right? So we can take the derivative of this, and this keeps constant. But there are radii there, distances. So this thing is constant only in the coordinate system fixed on the body. Because in any other coordinate system, because the body is moving, these r's will be changing. Right? And if r's are changing, this is changing. And if this is changing, then if you wanted to take the derivative of this thing when I is changing, you are in deep mess. Imagine taking the derivative of variable moments of inertia and things like this. So we come to the unavoidable conclusion. Anyone who have been telling you in the past 18 years to use inertial coordinate systems to do dynamics was not telling you the truth. The truth is that for any system of interest complicated enough, one needs to do dynamics in this coordinate system fixed on the body. Because only in such a system, this I remains constant, and therefore we only need to deal with derivatives of this part. So I have this written down on another slide, which looks like this. We must use coordinate system fixed on the body. Or to maybe make this a little bit weaker, coordinate system in which inertia matrix remains constant.